Oscillatory dynamics and topological bifurcation theory, or ODTBT, rests on a singular premise. The mass ratios of elementary particles are not free parameters that nature selected at random. They are geometric observables, derived from the structure of a high-dimensional coherence field. The entire framework operates through this single equation, the lock potential. By evaluating phase strains derived from Pythagorean triples, this formula accurately calculates the mass ratios of 9 distinct particles across both the lepton and meson sectors. This table shows the 9 validated particles compared to their particle data group values. At a specific electron baseline depth, denoted here as Ne equals 3, all 9 particles simultaneously achieve sub-percent error margins. To a graduate-level physicist, results like this immediately trigger skepticism. Highly accurate outputs derived from a complex formula often point to post-hoc curve fitting, where empirical variables are manually tuned until they match known experimental data. Looking at the lock potential, 3 specific variables invite this exact criticism. First, the golden ratio suppression factor, phi to the negative n. Second, the fact that leptons and mesons use distinct structural formulas. And third, the integer 3 used for the global electron baseline. For ODTBT to stand as a fundamental physical truth, we have to prove that these 3 empirical parameters are inescapable mathematical necessities. They absolutely cannot be mere statistical anomalies. The parameters within the lock potential are exact structural mandates. They are derived directly from pure group theory, real algebraic geometry, and game-theoretic topology. A companion paper addressing the framework's mathematics deconstructs these results. It details a rigorous approach for converting the empirical observations of the lock potential into topological law. We are going to interrogate the golden ratio, the dual formulas, and the baseline integer 3. We will cross-examine each of these empirical variables against a specific, established mathematical theorem. If these mathematical connections hold, the standard model's mass ratios cease to be free parameters measured in a lab. They become representation-theoretic eigenvalues calculated directly from geometry. We begin with the first structural question. Where does the golden ratio, phi, in the lock potential's suppression factor actually come from? We have to look at the alternating group A5. This group of even permutations of 5 elements is the exact mathematical isomorphism for the rotational symmetry of a regular icosahedron. This grid is the A5 character table. It charts the group's irreducible representations, providing the arithmetic rules for how icosahedral symmetry behaves. Notice the 2 exceptional 3-dimensional representations, labeled 3 and 3'. These representations are entirely unique to the A5 group. They do not exist for the symmetric group S5. Now isolate the 5-cycle conjugacy class, C+. This class corresponds to the precise rotations around the icosahedron's vertices. The character value of A5 evaluated on these 5 cycles is exactly phi minus 1. Because phi squared equals phi plus 1, the value phi minus 1 is mathematically identical to 1 over 5, the reciprocal of the golden ratio. Raising this character value to the nth power yields phi to the negative n. The golden ratio in the lock potential is not imported from nature or fitted to data. It is the exact arithmetic of icosahedral symmetry itself, evaluating its own vertices. This brings us to the second structural question. Why does the framework require a 3-component Pauli triplet to calculate elementary leptons, but a geometric mean for composite mesons? This dual architecture emerged empirically during the validation phase. Applying the meson formula to a muon produces massive error, while applying the lepton formula to a neutral kaon is overfitted. The formulas cross-test perfectly, but the structural difference lacks an immediate theoretical explanation. This wireframe represents a 6-dimensional mathematical space. According to the theorem of minimum embedding dimension, if you want to embed A5 icosahedral geometry into a periodic lattice, you strictly require 6 dimensions. Under the A5 action, the 6-dimensional module naturally splits. It decomposes into a direct sum of exactly 2 3-dimensional invariant subspaces. The structural correspondence maps directly to the physics. The three-component lepton formula mirrors the first three-dimensional representation. The meson geometric mean formula mirrors the second. In group theory, these two exceptional representations are mathematically exchanged by the unique outer automorphism of A5. The deepest division in particle physics, the difference between elementary and composite particles, is structurally synonymous with the outer automorphism of the icosahedral symmetry group. The final structural question addresses the baseline. Lie is n sub e equals 3, the unique depth that allows all 9 verified particles to hit their physical mass targets. At depth 3, the electron's phase strain lands within 0.054 radians of 3 pi. This specific near coincidence drops the lock potential to an anomalous minimum, scaling up the rest of the particle targets into the physically correct range. A critic looks at a 0.054 radian deviation and assumes it is a transcendental accident. The mathematician John Nash proved otherwise. Nash's 1952 theorem on real algebraic manifolds states that any smooth, transcendental manifold can be described entirely by polynomial equations. This means the 3 pi coincidence is an inescapable algebraic constraint hidden inside Klein's invariant ring. It is an algebraic property, not an accident. To understand the global optimality of the integer 3, we redefine the framework as a mass ratio game. The particles are players seeking their physical mass ratios, and the electron baseline is the underlying strategy space. This topology landscape maps out that strategy space. By applying the Kakutani fixed point theorem, which guarantees equilibrium in a compact convex space with upper hemi-continuous best responses, a Nash equilibrium is mathematically guaranteed to exist here. Kakutani's theorem provides the existence guarantee. The arithmetic of the 3 pi coincidence identifies the specific coordinate. The integer 3 is not cherry-picked. It is a mathematically guaranteed topological fixed point where the system's global consistency is perfectly balanced. This shadow grammar flowchart traces a 12-dimensional coherence manifold collapsing into a 1-dimensional lock potential. The mathematical threads map cleanly here. A5 group theory governs the icosahedron, Nash manifolds describe the 2D geometry, and Kakutani equilibrium locks the targets. It is necessary to state the exact epistemic level of these findings. The golden ratio identity is an established mathematical fact, verifiable directly from the character table. The Kakutani equilibrium is a rigorous mathematical reframing of the global consistency result. The dual formula split, however, remains a structural conjecture. It requires one final mathematical proof to graduate from empirical observation to representation theoretic theorem. Science requires exactly this kind of rigorous boundary mapping. We must distinguish between what is observed, what is conjectured, and what is mathematically irrefutable. The primary open derivation remaining for the framework is proving the A5 equivariance of the ODTBT coupling functions. Researchers must formally write out the explicit A5 action on the 2-seed phase space. This will prove definitively that the coupling functions transform cleanly under the group's representations. As this final derivation is completed, the entire lock potential is proven as a pure A5 character evaluation. The framework becomes entirely self-contained. Physical constants are no longer arbitrary numbers to be tabulated by machines. They are the eigenvalues of symmetric spaces. Under this framework, the fundamental mass of the universe is nothing more than the geometry of the icosahedron, evaluating itself.